say thank you for the invitation and for the opportunity to be here in Sao Paulo. It's the first time for me, and of course also visiting this institute. So I will tell you about some work I've been doing in recent years, which is about non-equilibrium stochastic thermodynamics. And this is work I am doing now at the University of Buenos Aires since 1.5 years now. But I started working on this in the University of Luxembourg when I was a postdoc in the group of Massimiliano Esposito. So first, I would like to give some context about, some historical context about our work. So let's look at this very simplified timeline of developments in non-equilibrium thermodynamics. So in the 19th century, we all know equilibrium thermodynamics was developed. And also, at the end of that century, the basis for the statistical, the microscopic counterpart of equilibrium thermodynamics was started to take shape. And one nice feature of equilibrium thermodynamics is that it is universal, but at the same time, the main principles and the main results only apply to equilibrium systems. To systems that are in equilibrium with its environment, and there are no currents circulating in any way. So if we go forward in time to the 20th century, then at the beginning of the 20th century, some results start to appear that apply to the linear regime close to equilibrium. So at the macro level, we have, for example, linear irreversible thermodynamics and the Onsager reciprocal relations. And in the microscopic counterpart, we have, for example, the fluctuation dissipation theorems. Okay, and this was more or less the situation for almost more than 100 years until the development or the discovery of the fluctuation theorems that maybe you have already heard about. The most famous are the Crookes and the Chernyshevsky relations. And these results were important because they were the first results of with thermodynamical meaning that are valid arbitrarily away from equilibrium. Okay, and so this started a wave of developments, a revolution in non-equilibrium stochastic thermodynamics that it is still ongoing. And nowadays we have many more results of universal validity that are also valid in contrast to equilibrium thermodynamics, arbitrarily far away from equilibrium. So for example, we have thermodynamic uncertainty relations, speed limits, generalizations of the second law, including information flows, and some other examples. Well, one feature of these new developments is that they are the level of description that they assume and the computational tools that we have at hand made them only practical for practical calculations at the microscopic level for systems that have few degree of freedoms or a low number of states. So one line of work I've been working on recently is taking those new developments in non-equilibrium statistical physics, in stochastic thermodynamics, and taking in some way some kind of meaningful macroscopic limit to be able to take those new insights at a more coarse-grained level of description, okay? And that is what I am going to talk about. So what is the fundamental problem of non-equilibrium thermodynamics? Well, typically we have a system that is out of equilibrium because of a couple of reasons. For example, it can be interacted with several reservoirs that have different intensive quantities, different temperatures, for example, and it can also be taken out of equilibrium because you drive it in time in some way. Okay, so the first observation is that we don't care, and we actually cannot control all the degrees of freedom in the system. We typically only care about the degrees of freedom in the central system, which is there with a green ellipse. And so the first step would be to seek a dynamics for the degrees of freedom we care about the central system. And the second step would be to attach to that dynamics a thermodynamic meaning, a thermodynamic interpretation. Okay? So there are two complementary approaches to do this.
One is the program of quantum open systems. Basically, this is a reductionistic treatment in which one assumes that one has perfect knowledge of all the degrees of freedom of the system and the reservoirs, and tracing out of the reservoirs, one can obtain a reduced dynamics for the system. And since one has, in principle, a priori knowledge, perfect knowledge of everything, one can identify very easily the thermodynamic quantities one is interested about. There is another complementary approach, which is working directly with stochastic descriptions of the dynamics of our system. So, and these are more phenomenological approaches based on Langevin dynamics or Markov-Chain processes. So, yes.
Can I say that the Markov-Chain process is the stochastic, let's say, classical version of the repeated interactions in the quantum, or?
Yeah, for me, it is more natural to think about it as the classical version of the Lindblad master equation.
I see.
Okay,
okay, but
yeah, but you can also cast repeated interactions formalism
right.
in that way. Yeah.
Okay.
Okay. So first, I work during my PhD. I managed to make some relevant contributions to the first approach, to the quantum open system approach. But during this talk, I will talk more about the stochastic approach, stochastic systems approach. Okay. So, but let me just mention a few things about the quantum open systems case. So what I did during my PhD was to consider an exactly solvable model of a quantum open system, which is...
Sorry, can I ask a question? It's
yeah,
sort
please.
of
Eduardo, yes.
At the level of the previous question.
Yes.
So in one case, you do sort of the full microscopic quantum mechanics of the problem. The second case, you do, it's like a Landau type theory in a sense. You take a microscopic system and you ignore all of these other effects, and you reduce that to solving stochastic equations. What is the role of quantum mechanics in that? Any?
I'm sorry, I didn't understand the question. I cannot hear you really well. Let me see if I can.
How does quantum mechanics relate to the second approach, stochastic?
Yeah, the first approach seems to take into account, the full quantum mechanics of a system of equilibrium. The second approach is purely classical.
Yeah,
what is the relation? What is the actual relation between these two?
Actually, this will be clear.
Is there a quantum version of the Langevin approach?
Well, actually, there are. It is not the I don't work with them, but I think there are quantum analogs of the Langevin equation. I mean, there you have all this quantum Ito calculus also, but this is not what I will talk about. Actually, you are right. The second approach is totally classical, and you can link it actually to a quantum treatment by introducing decoherence. So if you take the Lindblad dynamics and you neglect all the dynamics of the non-diagonal elements of the density matrix, then you end up with a completely classical Markov-Chain process, right?
Okay. Yeah.
And that is actually what I am going to talk about.
But I may also mention that the Lindblad approach is also approximate, because in a general quantum situation, when you integrate away the degrees of freedom of what you consider the reservoir or the bath, you get non-local in time interactions, and this Lindblad neglects, right?
Yeah.
So it's already an approximation.
Yeah. You typically need some kind of Markovian approximation and some kind of coupling approximation. Yes.
Right.
Yeah. Yeah. So is that okay?
Okay. I just wanted to know where you were in the universe. That's all.
Okay. Yeah. So during my PhD, I consider an exactly solvable model of a quantum open system that actually does not require those approximations, the Markovian approximation and the weak coupling approximation, to be solved. And this is because of the linearity of the system. So basically, what I consider is a network of harmonic modes, a network of harmonic oscillators, with some arbitrary quadratic potential that can be driven in time. And the network is also connected in different ways to different thermal environments. So this is kind of an extended model of quantum Brownian motion description. And some things that you can do with these settings is to study refrigeration protocols. So you drive the network in some way in order to extract heat from one of the reservoirs and dump it into the other reservoirs, right? So one important result of my PhD is that you can identify fundamental limits for cooling in this kind of linear quantum refrigerators. And actually, you can also link them to the generation of entanglement of quantum correlations in the reservoirs. So that is what we did in these first two works. And then we also use this formalism to study heat transport in ion crystals, depending on the geometry of these crystals. Also related to quantum open systems, recently, well, not so recently, but this is one of my last works on the quantum side of things. We identified the scaling properties of the work statistics across a quantum phase transition. Okay, so let me now go directly to start explaining the basic ideas of this, of stochastic thermodynamics. What are the basic assumptions? So I will explain this for the case of Markov-Chain processes, but you can do an analogous treatment for example, diffused processes, right? So let's consider that we have a system with a discrete set of states, and the dynamics on that discrete set of states is given by a Markov-Chain process. And so we can describe it by a master equation like the one I write here with some rates, transition rates, lambda nm, that gives me the probability per unit time to have a jump from state m to state n. Okay? Sorry? The various Pn. The Pn is the probability to be in state n at time t. I am not writing explicitly the time there because of simplicity. Okay, so now let's assume for the moment that we are describing a system that is interacting with a single thermal bath. So we know that at long time the system should arrive to a steady state that is at thermal equilibrium state. So it must be described by the Gibbs distribution. Okay, so this can be guaranteed by just assuming that, actually this can be proven. It doesn't need to be assumed that the rates satisfy the local little balance conditions. So the ratio between forward and backward rates, sorry, how do I do a light here? Here. The ratio between forward and backward rates are related to the free energy difference associated to the jump in this way, okay? And if this holds, then you can show that the steady state will be a thermal equilibrium state with zero net currents. So the net current along a given transition will be zero. Okay? And of course, that is right. That is what we expect from thermal equilibrium.
Sorry,
okay?
The lambdas have diagonal elements also, or no?
Sorry?
The lambdas, I just want to understand the lambdas. The lambdas are a zero if m is equal to n or not?
Yeah, if n is equal to m, it is like not having any jump, right? You remain in that state.
I'm just asking,
so
your definition is that it's zero?
It is zero. I consider them to be zero. Yeah. Okay. So this is the basic dynamics that we would assign to a Markov-Chain process that is representing a situation in which our system is interacting with a single thermal bath. Okay. Because we know that in that case we should arrive to a Gibbs distribution. Okay. Now what happens if our system is interacting with two reservoirs at the same time? Okay. And for example, it could also be taken out of equilibrium because there is some time-dependent parameter. So in this case, we can model the situation in the following way. We can think that the transition rates are a sum, a linear combination of the transition rates corresponding to the interaction with this reservoir and the transition rates corresponding to the interaction with this reservoir. Okay? Of course, in general, there could be higher order processes in which the system interacts in some non-trivial way with the two reservoirs at the same time, but this can be neglected, for example, in the limit in which the coupling with the two reservoirs is sufficiently low. Okay? Well, and so what we can see immediately here is that even if these rates lambda A satisfy a local little balance condition, okay, with the intensive parameters of reservoir A, and the same holds for B, the sum won't satisfy any kind of little balance. Okay? The ratio between forward and backward rates of the total rates won't be related in any trivial way to the free energy difference, for example, corresponding to that transition. So the system will attain...
Can't you find a detailed balance condition directly on the total lambda and get...
No, you cannot do that.
You cannot?
Yeah.
Is it straightforward to see that?
Yeah, it is well, maybe it is not straightforward from this slide alone, but yeah, basically what happens is that in this general case, the ratio between forward and backward rates you won't be able to express it as only a function of a difference of a state function, right? It will be a function of the transition itself. Mm-hmm. And that is the main difference with the equilibrium case. Okay? Well, and in this case, the system attains a steady state, but in this case, it won't be given by a Gibbs distribution, and also, it won't be true that the net currents along a transition will be 0, okay? So you will have circulation among states, you will have non-zero currents, which are, of course, characteristic of a non-equilibrium steady state, okay? Well, so let's recap the main ingredients of this kind of formalism. So we have,
I'm sure it's a triviality, but can I distinguish the equilibrium versus the non-equilibrium? Because in the equilibrium case, if I detach the reservoir, I will remain in equilibrium, while in the other case, I will lose equilibrium because there is the current, and if I detach the reservoir, the equilibrium is lost. Is it correct, this, or not?
Well, actually, yeah, you need, for example, let's consider this situation, right?
Right.
So if you run this for a long time, you will attain a steady state.
Right.
Okay, that will be a non-equilibrium steady state. And then if you detach this reservoir, you will attain a new steady state.
Exactly.
That in that case will be equilibrium, and the equilibrium corresponding to reservoir
Correct.
B.
Instead, in the previous case,
in the previous case,
I remain there.
Exactly, that does not happen. Okay. Well, so let us recap the basic idea. So we have a system with a discrete set of states. For each state, I can assign some thermodynamic properties. For example, the energy, the number of particles, the entropy of that state. And I have also stochastic dynamics over that set of states that I assume for simplicity to be Markovian. So it can be described in this way for some rates. And here is the most important part. I construct these total rates as a sum of transition rates, each of them corresponding to the interaction with a particular reservoir, thermodynamic reservoir, and each of these parts of the total transition rates satisfy local ideal balance. So they are related in some way, in this way actually, to the free energy difference along a transition. And also, this is an element that I didn't include before, but you can have work sources acting on specific transitions, right? And these are described by these terms. And you see here that if you have work sources, this is not actually detailed balance, because this is not a function of a state function difference, okay?
So, well, excuse me, yes. When you say this, you point something to the board, but we don't see it. Okay. So please be clear what you mean. What are these terms?
Computer instead of the...
no, sorry. Well, what I was saying is that in the stochastic dynamics, you have some net rates or net transition rates that can be split into contributions that represent the interaction of your system with a specific thermal reservoir, right? Which are these lambda A, lambda B, and so on. Okay?
Yes.
And you know, because you model in some way the interaction of your system when it is connected with a single reservoir, you know what is the local ideal balance condition for each of these individual parts, individual contributions, okay?
Yes.
That is what I said.
Okay, and W is what in this case, in the exponent?
Sorry?
What is, there's a W and M in the exponent. What does it mean? It's just a way of parameterizing this?
Yeah, it's a way of parameterizing. Here, basically, what you have is the connection between your dynamics, which is the net transition rate is what determines your dynamics.
Okay.
With
the W's are the same things that enter in your master equation or something.
Yes, for example, if you don't consider this splitting explicitly, you have no way of assigning, for example, a heat current specific to reservoir A.
or specific to reservoir B. You see? This splitting and the way these local rates, these rates specific to our reservoir, are connected to thermodynamic quantities is crucial if you want to track not, for example, the change in the total energy of the central system, but how that change in the total energy of the central system splits to the different reservoirs, you see? And that is crucial, of course, to evaluate the physical entropy production, okay? Because the way that those heat currents are split in the different reservoirs is relevant for that.
So this approach is only meaningful if the coupling to the reservoirs is actually weak, right? Otherwise,
yes. Otherwise, you could have higher order processes in which two reservoirs there is a process coupling simultaneously two reservoirs and a change in the central system.
Okay.
Yes.
Sorry, and Tx is a parameter for the moment that you introduce like this and you will fix later?
Tx, yeah, Tx could be, I wrote that case for simplicity, but Tx could be the temperature of reservoir X. X can be A, B, okay?
Ah, okay, X, okay, sorry, yes, fine,
okay.
fine.
So physically, you're thinking a situation, you have a physical system, and you have two reservoirs at different temperature.
Yeah.
And you want to see heat current across the system due to that.
Yeah, that is the simplest example, yes.
Thank you.
Yeah. Okay.
Just a matter of terminology. Now, adding W and M, do you still call that a detailed balance condition or not anymore because it's not a function of state anymore?
No, well, yeah, we still call it local detailed balance. Okay?
I see.
But
even though it's not anymore a function of state.
What happens in that case is that the appearance of these terms here. Sorry for the ones that are online. The question is about this contribution to the local detailed balance. So let's say that you have a single reservoir, but you also have external work sources. Okay. In that case, you won't reach Gibbs equilibrium C state. Okay.
Okay.
And actually, the deviation from the Gibbs C state will be given by those terms precisely.
Ah, okay.
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 Yeah. Okay. So just with these basic ingredients, what you can actually do is to derive the first law, which in this context is just a definition of what you consider heat, what you consider work. But you can obtain an energy balance in this form, and you can also very simply derive the second law of thermodynamics. So if you consider the internal entropy of the system as the Shannon contribution plus the average of the internal entropies of each state, in the case you have to consider them, then if this is your internal entropy, then if you sum the change in your internal entropy plus the equilibrium form of the entropy production in environments, so you have the typical expression, the heat over the interchange heat over the temperature, with a minus sign because we consider heat currents as positive when they enter the system. So this quantity accepts this very simple and nice expression, which is explicitly positive, okay, in terms of the total transition rates.
I have a question. In what sense is this an entropy?
Sorry?
In what sense it is an entropy?
In what sense S is an entropy?
Right. Entropy. So you modify the usual form of the entropy.
Yeah.
The entropy is a function of state. It doesn't depend on how you go from state A.
No, exactly. Well, but this is.
Yeah, it will depend on what happens.
This is a non-equilibrium entropy. You can evaluate. This is a main difference with usual thermodynamics. This entropy you can evaluate for any distribution. It doesn't matter if the.
How universal is this definition?
Sorry?
How universal is this definition? The definition in thermodynamics is universal. Yeah. That's the beauty of equilibrium thermodynamics.
Well, actually, one big part of my talk, actually my lecture on Friday is precisely about that. How universal is that? That definition. And we are going to see that it is pretty universal. So it allows you to
to say a lot of powerful things about the dynamics of your system. But maybe we can discuss this in a few slides.
Okay, thank you.
Okay, but I think your question actually points to a major difference between stochastic thermodynamics and classical thermodynamics, which is that in classical thermodynamics, entropy is only defined for equilibrium states. And here we can talk of entropy or free energy, for example, for arbitrary distribution. So you give me any distribution, it doesn't need to correspond to any Gibbs distribution. It could be a distribution for which the system has currents flowing, and you can still anyway assign an entropy to it.
I understand, but that means that you have to make some assumptions about the validity of these extensions.
In my opinion, all the assumptions are laid down already. I don't know exactly if I need something more. Maybe there is.
That is my
maybe
question.
I am missing something, I don't know.
I mean, you know, all equilibrium states are equally happy, or non-equilibrium states are unhappy in their own ways, as in Anna Karenina. But so it's a question how generic this is, or this is a specific class of non-equilibrium.
This is a definition. This is a definition, and it is fully generic as far as I see. And then we can ask what are the properties of this definition. Okay.
I understand. You can do this. The question is, are there things that are not included in this definition?
I don't know really. I am a little confused by the question.
Well, it's a question of the universality of the description. That's what I'm trying to say. Or rather, the generality of the description, since Sn presumably has to depend on some microscopic properties, I assume.
Well, if your description is sufficiently coarse-grained for each of the states that you are considering your Markov dynamics to have an internal structure, then that is the point of assigning an internal entropy here, to each of those states. But that you consider this in this average, you see? This average is not only the Shannon entropy. It is the Shannon entropy plus the average of the internal entropy of each state over the given distribution. You see? So, and here, here there is an important condition. Thank you for the question. Here there is an important condition.
How is Sn defined? That's my question, I guess.
Yes. There is an important condition here, which is that in the case the discrete states that you consider have an internal structure, and therefore you have to assign an entropy to it, those degrees of freedom that you coarse-grain, and you put a global label, which is the label of your state, those degrees of freedom should be at equilibrium. They cannot be out of equilibrium.
Okay.
If this happens, then your description is not valid, or at least it will underestimate the total entropy production. But as long as there is, the degrees of freedom that you coarse-grain for each of your coarse-grained state to have an internal entropy, as long as those degrees of freedom are at equilibrium, then you are fine. And this can be justified, for example, with time scale separation assumptions.
So there is an assumption here that the processes are sufficiently slow so there is local equilibrium?
Over your coarse-grained states, yes.
Okay.
Okay. And here, I am realizing now there is an important mistake in this final equation, which is it should include a sum over x, and the lambda should be the lambda x, not the global ones. Okay? And this is crucial. I am ashamed I did this mistake, but okay, let's continue.
Yes. X appears on all the lambdas that appear in
the in all the lambdas you have an x, and here you have a sum over x.
I understand.
Okay? And that is why this splitting is important. Okay? Cool. So, so let's mention a few general things. So this formalism is extremely simple, extremely schematic and modular, but it allows you to obtain in a very simple way a lot of universal and powerful results. For example, the first one, and also historically the first ones, are the fluctuation theorems, can be obtained very easily in this setting. More recently, people have discovered the thermodynamic uncertainty relations, which I don't have time to explain, but they are very interesting. You also can derive speed limits. You also, if you consider bipartite systems, you can obtain generalizations of the second law that include information flows. And you also can obtain new results about the steady-state thermodynamics. So yes.
I have a question, because from what I know, the speed limits are, I mean, maybe I'm ignorant of a piece, are defining the quantum regime. I know the quantum speed limits.
Yeah, these are thermodynamic speed limits, and
so
they are actually related to quantum speed limits, and there is a very nice work that actually connects the two of them.
I see.
But these are physically they have a completely different meaning.
Okay,
this
so
apply
later,
this apply to Markov.
Later, give me the paper.
Yeah, we can talk later.
Thanks.
Yeah. Okay. And also, you can derive these very powerful and universal results that are varied arbitrarily away from equilibrium. And this kind of formalisms also found very impressive applications in different fields. For example, chemical reaction networks, cellular signal and sensing, electronic circuits, both at the nano and the mesoscopic scales, molecular motors, and some others, even finance, for example. Okay, so and this, as you can see here, this is a search I did some days ago when I was preparing the lecture. Stochastic thermodynamics, this keyword is starting to emerge as an important keyword in the literature, and here you see how it is getting into the books in the recent years. And this is a search over books that Google offers for free. What I will talk, and this is where my talk actually starts, the talk about my own work at least. I will talk about new results in steady-state thermodynamics and also applications of stochastic thermodynamics to electronic circuits. Okay, so first place I will talk about this article that was published already 2 years ago that I did with Massimiliano Esposito in the University of Luxembourg when I was a postdoc there. And it is about an extension of the usual second law of thermodynamics that applies to non-equilibrium steady states. Okay, so the detailed proof of this result, and actually a proof of an extended version of the result we published here, this is what I will do on Friday. Okay, so I won't give the details today, but I will explain the main features of the result. So this we already discussed. So suppose we have a system that is interacting with a single thermal reservoir. So this system, we expect it to arrive for long times to equilibrium state that we know how to describe. So the Gibbs distribution tells us that if we are in an equilibrium steady state, if we measure the state of the system, we will see the state X with a probability that decreases exponentially with the energy of that, or the free energy in a generalized setting of that state, right? Over KT, okay, where T is the intensive parameter describing the reservoir. Okay, so we know how to describe this. This is a very old result. This is the Gibbs distribution. So what happens if we go to a non-equilibrium setting? If now our system is interacting with two reservoirs, reservoir A and reservoir B, okay, and we assume that the system also attains as a steady state, what is the generalization of the Gibbs distribution in this case? If we measure the state of the system, how can we describe the probability of the result? Okay, this is a very basic question, and very little is known about it. So there is early work by Leibowitz and McLennan, but in general, very little is known about this function. So that we will call so basically, since the probability is positive, we can always describe it as in terms of its log of minus its log, which is this function that is called the self-information. So a very basic question is, what measurable physical quantities determines that self-information? Okay, and a related question is, how can we easily compute it or approximate it? Okay. What I will show you is that we were able to say something new, simple, and useful about that function, the steady-state self-information. Okay, And the results looks like this. So a first important comment I should make is that it applies to systems that are stochastic but have a well-defined macroscopic limit, okay? And in that macroscopic limit, there is a deterministic dynamics that emerges. A very common example is chemical reaction networks, right? Imagine that you have a vessel with some solvent, and in that solvent you have some chemical species that they can react with each other to form new molecules, okay? So, and in that case, your description is the number of molecules of each species. Whenever you have a reaction, you have a jump from some configuration, number configuration, to another number configuration, right? When you remove some kind of product species and you add some kind of reactant, okay? Well, if you have that system and you take the limit of the volume of it being large enough, then the deterministic, then the dynamics of the concentrations of the chemical species follows a deterministic dynamics, okay? So let's consider a trajectory, a deterministic trajectory that is a solution of that deterministic dynamics, right? And that this trajectory connects an initial state, x0, to a final state, xf, okay? So the usual second law of thermodynamics tells me that the dissipation, the entropy produced along that process will be positive. And that entropy, you can, for isothermal systems, you can express it as the work that was done by external sources during that process minus the free energy difference, okay? Between the final and initial point. This is the usual second law that tells me that this quantity should be positive, okay? Well, what you can do is to derive the following results that tells you that the sum of the same quantity that appeared before, which is just the temperature times the entropy produced along the trajectory, plus kBT times the difference in steady state self-information between the final point and the initial point, that is also always positive. Okay? Sorry?
I thought your initial goal was to define what is ISS. Here instead you are giving constraint on what it is without...
I already defined ISS. ISS is minus the log of the steady state probability distribution.
Okay.
And now I am saying something about it.
Okay.
Okay? And what I say is this, is that over...
you're assuming that at steady state there is a quasi-equilibrium?
No, I am not assuming anything. The steady state can be arbitrarily far away from equilibrium. This is fully general.
What is ISS? How is ISS defined?
Okay, I say it again. ISS is, so you have an steady, what I am assuming is that there exists a steady state. That steady state will have a probability distribution. ISS is minus the log of that probability distribution.
Okay.
Okay? Well, and this is a completely general result. This is valid for any stochastic system with a well-defined macroscopic limit. I derive it in that work for Markov-Chain processes, but it can also be derived for diffusive processes, and this is something we will publish soon. Okay, and let me discuss some features of this result. First, it was already known, something that was already known about this function is that it is a Lyapunov function of the deterministic dynamics. So over any deterministic trajectory, it always decreases, okay? That means that this term that I added here is always negative. And therefore, that implies that this should be positive. Is the sum of the first term plus the second term that is negative should be positive, then the first term should be positive. So this second line, this generalized emergent second law is a stronger condition than the usual second law, and actually implies the usual second law. Okay.
Sorry, what is a Lyapunov function?
Sorry?
What is a Lyapunov function?
For a general dynamical system, a Lyapunov function is a function that has always, the derivative of a function has always the same sign. Conventionally, you can take it to be negative, so it's a function that always decreases over that, along that dynamics. And importantly, it is also bounded.
by below.
It's not related to the Lyapunov exponent in a
it is not directly related to the Lyapunov exponents. It is just a function that tells you that there is some kind of time asymmetry in your dynamics.
Okay, good.
Yeah. Okay. So another important property of this result is that the inequality gets saturated, becomes an equality in the linear regime close to equilibrium. So in a linear regime close to equilibrium, this allows you to actually estimate very precisely this function, or at least differences of this function. Okay? Actually, for systems that have fixed points attractors, then you can get the rate function without
Actually,
any
it
problem.
might be related somehow to the Lyapunov exponent, because also the Lyapunov exponent tells you something about not really time reversal, right? You do a small perturbation, you do evolution, then you do the small perturbation back, and you come back in a completely different point.
You're right, but I don't...
So maybe this guy is at least morally related to the Lyapunov exponent.
Yeah, I think that if you know the Lyapunov exponents, maybe you can say something about the existence of a Lyapunov function. But I mean, the Lyapunov function is also not uniquely defined. Okay, whenever you have a system with some time asymmetry, you have many Lyapunov functions. Okay, this is one. Okay.
So the Lyapunov exponent is usually is a necessary condition, not for chaos. And I wonder whether it's related to. That's why I asked.
Okay. Well, I don't know much about chaos and so nonlinear dynamics in general. So
chaos is supposed to be related to equilibrium in the end of the day. That's why I wonder. Okay,
yeah. Yeah. This goes a little beyond what I know, really.
Okay.
Yeah.
Sorry, I have a silly question. Why is Boltzmann constant in one of the terms and not the other? There was some difference in the definitions that put in the Boltzmann constant?
Well, here you mean?
Yeah.
Well, this is a free energy, so it already has units of energy.
Okay, so you just defined your ISS to be...
Yeah, I is just is a dimensional because it's just the log of the probability. Yes. Okay. So so it has this second property, which is that the inequality becomes an equality. But in general, even if you are very far from equilibrium, this allows you to obtain a bound on this difference only in terms of the deterministic dynamics. And that is very powerful computationally. Because the alternative methods to obtain information about the steady-state distribution are very, very heavy. Right? You need to either run Monte Carlo simulations or, for example, the Gillespie algorithm in the case of a chemical reaction network, or you need to write down the master equation in some matricial form and employ spectral methods, for example, computing a particular eigenvector of the generator of the master equation, and that is also always, of course, limited to systems with a limited number of states. And this result allows you to obtain information about the steady-state distribution only in terms of the deterministic dynamics, which is almost trivial to integrate. Okay? Yes.
I disagree with that. Because this is like, if you do a general dynamical system,
yes,
quantum or classical is not integrable, and therefore it depends.
Well, no. Well, I meant numerically.
Yeah, even numerically.
Okay.
There is a question. The assumption that something is deterministic is not sufficient because it can be chaotic.
I see.
So the question is to what degree of precision. And now the initial for oscillators we can always do it, okay?
Yeah.
But not for a general case.
No, I completely agree with you. I actually going into chaotic systems or even systems with limit cycles is something that we are working on at the moment. Actually, we are working on limit cycles. So far, we have used this result only for systems that have fixed point attractors, okay? Mm-hmm. And the deterministic dynamics is actually kind of simple. But you're right that the deterministic dynamics can get very nasty also. And I have no comments about that really so far. What I can tell you is that in the systems that I studied,
solving the other two approaches that I mentioned, the Monte Carlo simulations and the spectral methods, are far most costly than this alternative. That is for sure, and I will show you an example. I will show you an example later.
Okay.
Okay. Well, so the proof of this result, which is I think very nice, I like it a lot, is what I will explain on Friday. Okay. Now I will continue. So I want to show you an example of application of this. So for this, I need to tell you a little bit about this other work that we did some years ago, also with Massimiliano Esposito in the group of Luxembourg, and Jean-Charles Delven, a collaborator in Belgium, which is about the stochastic thermodynamics of nonlinear electronic circuits. Basically, here I would like to make a few comments. So historically, in statistical physics, there has been these questions about the thermodynamics of information processes. You know, all the Landauer bound, the results by Bennett, and so on. And these questions were re-examined, let's say, in recent years in the fields of stochastic thermodynamics, but only at a very abstract level and always playing with toy models. Okay, but what we wanted to do with this work is to close the gap between those abstract developments in statistical physics about the thermodynamics of information processing and concrete problems in electronic engineering. So we wanted to apply stochastic thermodynamics to realistic models of the kind of circuits that are actually used to make computers nowadays. Okay? And this is the result of that work, which is also very nice, in my opinion, and I will tell you a little about it. So, let's consider this circuit. And I will explain in the next slide what this circuit does. But for the moment, it is just a network of conductors connecting. The conductors are these lines connecting transistors. The transistors are these guys here. Okay, and these are most transistors, metal oxide semiconductor transistors, that come in two types, and they are connected here in a complementary way. That is the origin of this word CMOS. And this is the dominant technology to build computers. And actually, this specific circuit, is how you implement a bit inside a processor inside this computer. Okay, it is actually exactly the circuit how it is implemented. So basically, we want to describe this circuit at a stochastic level, right? We want to be able to model the circuit in a way that tracks the thermal fluctuations occurring in it, and that in a way that would also allow us to say something about the thermodynamic cost of operating this circuit. Okay? So the approach is very simple. What we do is to map the circuit to a set of conductors. Some of the conductors, the conductors are these blue shapes here, and some of the conductors are free. Some of the conductors are regulated by voltage sources, and then you have conduction channels between these conductors that are labeled here A, B, and C. So, okay. So once we think about our circuit in this way, we can identify the state of the circuit, and the state of the circuit are simply the number. The configurations in which you specify the number of charges, of elementary charges, inside each conductor. Okay? Alternatively, you can give the value of voltages of each conductor, which is an object with a well-defined voltage along all the surface. And we know from basic electrostatic theory that the energy that one should assign to each of these configurations is a quadratic form of either the voltages or the charges. Okay? So once we have identified the set of states, we can also identify the energy for each state. We can write down a master equation that gives me the dynamics of the probability distribution over this set of states with some rates, where each rate is associated to a particular conduction channel. And the specific functional form that you should assign to each transition rate can be obtained in a systematic way only from the characteristic IV curve of the particular device. For example, you might have a conduction channel, might be a tunnel junction, it might be a diode, it might be a transistor. Each of these devices have different IV curves, but if you give me the IV curve, if I combine the IV curve with the local little balance condition that I showed you before, you can obtain a specific form for this transition rate. And in this way, you can construct a dynamics with an attached thermodynamic interpretation, which is thermodynamically consistent. And this is important because many models that are used in engineering actually lack thermodynamic consistency, and they are prone to systematic errors. For example, non-zero currents at equilibrium, okay? Non-zero entropy production at equilibrium. Okay.
Sorry, what is rho?
Rho, sorry, yeah, this will be clear later. No. Rho is a particular transition. For example, rho is a transition that takes my charge configuration from Q to Q plus delta rho. Well, delta rho is a fixed vector. For example, let's say that you have a jump from conductor, a jump of a charge from conductor 1 to conductor 3. So delta rho will be a vector which has -1 for conductor 1 and +1 for conductor 3. That is a vector, okay? Yeah. Yes, I don't want to enter into the details. The important thing is that basically what we do is to assign a Markovian evolution to describe the dynamics of this circuit. Okay, and okay, so what can we do with this formalism? For example, let's consider, as I was telling you before, the way bits are actually represented in actual computers. So basically, the construction is like this. You take two NOT gates. Each of these triangles is a NOT gate. This is a logical circuit. If the input is true, the output is false, and so on. Okay. If you connect two NOT gates in a loop, that is you get a logically B-stable system, right? That has two true configurations, let's say. False true, true false, okay? And it is locked in those two configurations. Okay, now the trick is to implement each of the NOT gates in some technology. For example, in the CMOS technology, the NOT gate is implemented, sorry for the ones that are online, is implemented like this configuration of a PMOS transistor and an NMOS transistor, okay? So this circuit, as a physical system, has 2 degrees of freedom, which are the voltages here, V1 and V2. And if you compute the steady state, either at the deterministic or at a stochastic regime, you compute the steady state of this circuit, you will see that there are 2 stable states that correspond thermodynamically to 2 metastable non-equilibrium steady states. Actually, there is so for example, if you take the master equation and in some way, for example, Gillespie simulations or spectral methods, you compute the steady state, you see that when the power in voltage, this symbol here, VDD, is the power in voltage, and here below you have minus VDD, so you have symmetric powering. When the power in voltage is low, so you are in a regime close to equilibrium, the steady state is monostable, has a single, is a unimodal probability distribution. But when you increase the power in voltage, there is a second order phase transition into a B-stable steady state. Okay? A B-modal distribution for the steady state. And this is, of course, what allows you to store a bit of information in this system. Okay? And, well, so, and as I was mentioning before, computing the steady state of this is not easy. For example, here I am considering, I forgot to put that information, but here a voltage scale that appears here that in some way controls the scale of your system is the elementary voltage, which is the charge of an electron over the typical capacitance of your circuit. That, for this case, is around 0.1, the thermal voltage. And so for this steady state, we have in each axis, we have around 300 states. So my full state space is of the order of 300 square, right? And that is already a big matrix. And so the generator of the stochastic dynamics has that size, which is already big. And to find an eigenvector of that is computationally demanding. So imagine if you had a circuit with only one more degree of freedom, only one more voltage. Okay? The spectral method is out of the way. You cannot use it. Okay? It's too demanding. The Monte Carlo simulations are also demanding. You need to run them for a long time if you want to sample the steady state well. And actually, there are some works in engineering in which they care a lot about the error rate of this memory. And to estimate the error rate precisely, they need to run simulations sometimes for a month. Okay? So these are expensive methods. And what I will show you is that if we use our immersion second law for this kind of problems, we can get a quick answer to this. And this is what I show here. So here I have the same circuit, the same steady state, but now I consider deterministic dynamics that starts somewhere in the steady space and relax to one of the fixed points. Okay? I can consider this deterministic dynamics, this deterministic dynamics, this deterministic dynamics. Okay? For different initial points, I will have different relaxations to the fixed points. Okay? So the immersion second law that in differential form takes this expression, but okay, you can express it in this way as I decided to do before. So the rate function at the initial point will be, to linear order in equilibrium, the rate function at the final point plus the entropy produced along the trajectory. Okay? For long times, if your trajectory is long enough, this final point will be the fixed point because all the trajectories end up there, right? So here you have a fixed quantity, which is the state function, the self-information at the fixed point. Here you have your unknown, which is the self-information at the initial point. And the only thing you need to do is to integrate the entropy production along the trajectory. Okay? And if you do this for the system, you can do the reconstruction based on the deterministic dynamics, assign to each point along the deterministic trajectories an estimation of your self-information, and from the self-information, you can reconstruct the probability distribution. Okay? And as we see here, it works, for this case, remarkably well, which means that I am not showing the results of that, but which means that you can estimate the error rate of a memory like this very cheaply. Okay? Okay, so I am close to the end now. I would like to mention some ongoing and future work that I have in mind for in the short term. First, the immersion second law I told you about is actually a general property of Markov processes, of Markovian processes that are microscopically reversible. Okay, that means that if a jump in a direction is possible, the reverse jump should also be possible. So if you have a Markov jump process or diffusive process that respect that property, then the immersion second law, and also has a well-defined macroscopic limit, then the immersion second law holds. And actually, you can use it also for systems that have no relation at all with thermodynamics. Okay? One example of such systems are population dynamical models, okay, in which you track the number of individuals of a given species, okay, and you model that dynamics based on the interaction between the different species and the...
Sorry, before,
yes.
I understand you're going to talk about this, but before you just start doing this new thing, can I just ask, does anybody have any questions about what he talked about
please.
before?
I will ask if I can attend on Friday. I will ask, but not now.
Okay, yeah, that would be great. Yeah.
Okay, go ahead.
Okay, so as I was saying, the emergence law is a general property of Markovian dynamics that are microscopically reversible, and so we can apply it to a lot more, or to a lot of different problems that are that not need to be related in any way to thermodynamics. And an example of that is population dynamical models, in which you track the number of individuals of different species and model that dynamics in terms of interactions between the species. So a very popular model to do that is the Lotka-Volterra equations, in which species interact in this kind of quadratic or bilinear way with each other. And you can see very easily, this is anyway this is clearly a nonlinear dynamics. And you can see that if this interaction constant between species are symmetric, then you can cast these dynamics as a globally detailed balanced dynamics. Okay, as you can cast these dynamics as the relaxation of an equilibrium system. Okay, but if this interaction between species are not symmetric, then if you look at these dynamics from a thermodynamic standpoint, then the system is out of equilibrium. So in the first case, computing the C state is trivial because you can derive from these dynamics. You can assign to that dynamics a Hamiltonian, and then you know that the equilibrium will be the Gibbs distribution corresponding to that Hamiltonian. But if these constants are asymmetric, you cannot do that. There is no guiding principle telling you what will be the C state. So this is another possible application of the Merton-Second law I told you about that we are working on with Gianmaria Falasco at the University of Padua. Well, another line of research.
I can't follow.
Yes.
NI are just I are the different species. Is that what the I in
yeah.
I is?
So
the way you wrote it, it's obviously the antisymmetric part doesn't appear. I don't understand what you mean by that. Alpha ij, if it contracts with ni and nj.
You're right. You are completely right. I don't know what is missing there now.
I think you have an ni too many in that term, right?
Yeah, you're right.
You have to erase one of the ni's. Yes.
Thank you. Actually, yeah. This doesn't make any sense. Actually, you should remove this ni here. And actually, that is a term that appears in the Hamiltonian, of course. Yeah, sorry for that. Yeah. So, yeah, thank you. Okay, so another line of research is related to the article I told you about applying stochastic thermodynamics to nonlinear electronic circuits. So something we did in that article, but I didn't discuss, is that you can actually use that formalism to design circuits that are stochastic, that have some stochastic way of working that is in some way controllable. So something that you can do is, for example, if you add this little modification to the usual circuit that you use to implement a bit, you can implement a probabilistic bit, which is basically a generator, an asynchronic generator of random bits, in which you can control the bias with which you generate those bits. And this is something that for me is also very interesting, but I didn't have time to discuss, that if you have an array of many of these probabilistic bits, then you can implement in a hardware, based on hardware, many different algorithms for a stochastic sample or Boltzmann machine or machine learning, for example. And this line of thought, let's say, is actually becoming popular now. There are a couple of companies that are interested in this idea that they are calling thermodynamic computing. And there is one of them, Extropic, that actually was interested in this work and with which I will collaborate in the next few months at Boston with this guy, Trevor McCord, which is one of the founders of this company. And another area in which I am working on is chemical reaction networks. For example, we have this recent article in which we apply ideas of circuit theory as it is done in electronics, but we apply them to chemical reaction networks. Okay, So now I would like to mention some of the work with tutoring and direction of students. So in Luxembourg, I had the opportunity to tutor different students of the group. With Ashwin Gopal, we work on large division theory for noisy nonlinear electronics and thermodynamics of timekeeping. With Shesha Gopal, we are working now on percolation problems and dynamics in random chemical reaction networks. I'm very excited about this and will appear soon on arXiv. With Massimo Bilancioni, we work actually on implementations of Maxwell daemons or information engines in chemical reaction networks. So in Buenos Aires, I am currently working with a master student, Tomás Correa, on dynamical large division theory in full phase space, because something I didn't discuss, but an important feature of Markov-Chain processes is that they are in some way overdamped. They cannot display oscillations if the dynamics is detail balanced. So we are extending the emergent second law to systems that have also inertial degrees of freedom with him. So some final comments regarding the emergent second law. So the emergent second law can be generalized. I show the expression of the emergent second law for non-equilibrium steady states, but it can also be generalized to time-dependent states, to evolving states. And this is something that will appear also soon on arXiv. And actually, the proof I will show on Friday will be about this version, which is a slightly more general than the one I discussed today. Okay? It can also be derived for general diffusive processes. Okay, and as I mentioned, since it is a general property of Markovian processes, it can be actually applied to many other problems that have no thermodynamic meaning. And regarding to electronic circuits, as I mentioned, our work aimed to close the gap between abstract developments in thermodynamics of information and concrete problems in electronic engineering. And in that sense, it was, I would say, very successful. And it provides the basis for the study and design of novel computing schemes where thermal fluctuations are actually exploited as a resource. I didn't talk about that, but if you have questions, I would be happy to explain a little more about it. And for example, it was used to design a probabilistic bit, which is a basic building block for stochastic annealers. And this is actually one of the first goals in this emergent field of thermodynamic computing to actually build one of these thermodynamic stochastic annealers. And this is what I will start thinking about during this year in Boston. So this is a list of references and selected works, not exhaustive. And I think that is all. Yeah.
Start with questions from the people who are online. Anybody on the Zoom?
I have a question. So I'll use the example of the Lotka Volterra because you have it nearby, but it also applies to the other ones. So in the Lotka Volterra, you have different phases, right?
Yes.
Depending on the parameters. So with your formalism, how do you see the transitions between those phases? Do you see them?
Yeah, actually, for example, something that you can have, and actually the Lotka Volterra dynamics is famous for, is limit cycles. Okay?
Mm-hmm. Yeah, right.
Well,
yeah.
when you have so I won't be able to apply my emergent second law to limit cycles. So that is out of the way. Also, chaotic dynamics is also out of my scope for the moment. Okay. What I can apply my formalism to is the phases in which you have fixed points attractors. Okay. And in that case, a phenomenology that you have in this kind of population dynamics models is transitions between these different fixed points driven by noise, by demographic noise, right?
Yeah.
Well, one thing that the emergent second law could be very useful is in bounding the transition rate between between two or more fixed points. Okay, so this would be, for example, in that area, people talk about the probability of massive extinctions, for example. Okay, so so the probability per unit time to experience a massive extinction is something that can be bounded with the Mercian second law. But you are right. This is an application that only has to do with the simplest kind of attractors. I don't know if I answered your question.
Yes, yes, you did.
Okay.
And the other question is about the multiplicative noise that you have in this equation. So,
yes.
Can you deal with it? Because it's
we can actually the generalization of the Mercian second law to diffusive dynamics is transparent to that. You can put any diffusion tensor.
Okay.
Yeah.
Okay. And what about non-Markovianity? Because in equilibrium, for the dynamics, Langevin dynamics with kernels and so on, if equilibrium conditions are satisfied, then you go to equilibrium as well, and you have the same Gibbs distribution, right? While here, doesn't seem to be easy to deal with that.
Yeah, no, totally. I am not able to say anything about non-Markovianity. Yeah. I am also not planning to explore that direction, even if I recognize it is interesting. I think for the moment I will remain on the Markovian scenario.
Okay.
Yeah.
Then I have a curious question. So, what are Gillespie simulations?
Gillespie simulations.
Yeah.
The Gillespie algorithm it originated in the context of simulation of chemical reaction networks. So I think it is from the 60s and the 70s, and it is the state-of-the-art algorithm to simulate chemical reaction networks at the stochastic level, and it is basically a continuous time Markov chain. It is just that. Yes.
I see.
It has that name in the context of chemical reaction networks. Yes.
Okay. Yeah. Thank you.
I have a general curiosity.
One second, Dario, let's just see if there are other questions online. Any other questions from people online? Okay, go ahead.
Okay. I think it's pretty, people in quantum, we are, let's say, keeping investing and spending efforts and so on in quantum computing because the promises are amazing.
Yeah.
In this thermodynamic computing, what are the promises?
The promises are to, you don't have promises about computational advantages regarding what I mean is that you don't expect to solve problems with a computational in a computational time that is orders of magnitude below what you can do with a usual computer.
So let's say
you are not expecting that.
You don't have a sure algorithm like for
you don't have that.
Okay.
What you expect is to attack problems that are inherently stochastic in a thermodynamic efficient way, consuming way more or less energy that you could spend if you try to attack those problems in a regular computer. Okay. Regular computers, the simplest way to argue for this is the following. Regular computers are deterministic devices. They are resilient against noise, okay? And actually, to be resilient against noise, they need to pay a thermodynamic cost. They need to operate with voltages that are high enough to be resilient, to be actually resilient about thermal noise, because you don't want them to fail even once, even a single bit.
Okay.
Okay, because that could ruin an entire computation, right? Okay. So, but there are a lot of problems that are of a stochastic nature. Okay. For example, in machine learning, every day people use a stochastic gradient descent.
Sure.
To train a neural network, for example.
Okay.
For those applications, you need to generate random numbers like crazy. You need to generate a lot of random numbers very fastly.
Instead, this
and it takes a lot of energy. And this is paradoxical because you are making your device resilient against noise, to later use it to produce a lot of noise.
Okay, I see.
Okay, why not instead use the intrinsic thermal fluctuations, you see, that are present in any physical platform, and try to tame them, and to shape them in order to solve a particular problem you are interested in. Okay, that is the field of thermodynamic computing.
Just for fun, for example, weather forecast will become better because it's intrinsically noisy, and you can use.
That is, I would say, very far on the.
Exactly. Okay.
Yeah.
So,
But,
what are? I mean, quantum computing is waiting from like 50 years because we know that, let's say, quantumness is very, how can I say, fragile. So you lose you have the coherence essentially. What are here the main challenges? To make this
the main
thermodynamic...
challenges are precisely to be able to control the noise, to tame it, to do what
I see.
To
so
do
you are
what
too
you
noisy.
want. Yes, exactly.
I see.
So and do that also in a thermodynamically efficient way, because you can do that very easily at a macro scale, but of course paying a lot of energy.
Okay.
If you want to reduce the thermodynamic cost, you need to control the noise at very small scales.
Okay.
Okay. Actually, I have a slide about that, but I don't have time to explain it. But you can. There is a simple scaling argument that tells you that if you want to control the noise, you need to actually work with the state-of-the-art fabrication processes. You know, the ones that are going to be used for the iPhone in 5 years, for example.
So if you have to bet $1, you bet will arrive first quantum computing?
Well, actually, let me tell you something. I became disenchanted with quantum computing a long time ago.
Okay.
But so it is not a surprise for me. But this guy, Trevor McCord, and his partner, which are the two founders of this company, they were quantum engineers at Google.
Okay.
Both of them were quantum engineers at Google.
And then they moved out.
And then they got tired of the quantum promise, and they started thinking on a different line. Yeah.
Okay, thanks.
Yeah.
So I had a question about the population dynamics. I know you didn't talk about...
Sorry?
About the population dynamics.
Yeah.
You claim this is a theorem. Maybe I don't know what you mean by equilibrium, but you have a theorem that says that if alpha ij is symmetric...
Yeah, it's very easy to prove. Yeah. I mean...
And if and only if? So if it
basically, let me tell you just, I mean, if alpha ij is symmetric, you can write this part of the equation, this part here, as the gradient of a potential. It's just that. And yes.
So I'm thinking about the physics of I have a species that, I have two species that are, let's say I just have two. So you claim there can't be equilibrium unless they have an equal, unless alpha.
Yeah,
alpha
that means
1, 2
that.
Is alpha 2,
yeah,
1.
exactly. That if this matrix is symmetric, it means that if the presence of a species, of a particular species, is beneficial for a second one, then the presence of that second one is also beneficial for the first one. You see?
Yeah. So this is a new result, or this was well known? Or
No, this is well known. This is well known.
Okay, not by me. Okay.
Yeah.
So those are the only equilibrium systems where you have those are the only equilibrium systems. You can't have equilibrium systems.
The claim is that if you have a Lotka-Volterra dynamics like this, where this matrix is symmetric, then you can think about it as a relaxation in an equilibrium landscape. That is the claim.
Okay, let me think.
We can discuss it later. Yeah.
Any other question?
Okay.
Okay. So let's think. No.
Thank you. Bye-bye.
Bye. Thank you.
I guess we can go